And hit record. Hi everyone. Happy September. Thanks for joining it. Thanks for dialing in. So today our featured presenter is Conor Hayes at York University. And they're going to be talking to us about some recent work investigating micro ultra cold traps on the moon. And so Connor, I'll let you pull up your slides and introduce yourself in more detail if you should so wish. And then I'll let you take it away. A reminder to everyone else to just have your mics on mute unless you don't, unless you're actually trying to say something. And also, so question for you, Connor. If people have questions, do you prefer that they hold them until the end, or do you prefer answering questions as we go along? Up to
I
you.
do usually prefer them having at the end, but if there's like anything like super pressing that's, stopping
Mhm.
anyone's comprehension of what I'm saying, then feel free to speak up.
All right, sounds good. So with that, I will put myself on mute and let you take it away.
All right, there we go. That should be shared now. Um,
Yep, looks great.
Great. Well, hello everyone. Thanks for having me. My name is Conor Hayes, and I am a PhD student at York University in Toronto. And today I'm going to be talking to you about my work examining these topography-enhanced ultra cold trapping at the LCROSS impact site. And so this work actually formed part of my master's thesis and has recently been published in JGR Planets. So before we dive straight in, I'd like to talk a little bit about some background information. I mean, I assume that most of the attendees here are probably familiar with a lot of this information, but I still like to set the stage before we really get started. So we're now in this, this Artemis era of lunar exploration, which has really been focused on the moon's permanently shadowed regions, particularly near the South Pole. And this is due to their ability to act as these cold traps where volatile molecules like water can resist sublimation over geologic timescales. So these volatile deposits are of interest both due to their scientific value as well as their ability to potentially support long-term crewed missions to the lunar surface through in situ resource utilization. And so with this interest in mind, there have been a number of attempts over the last decade or so to survey the volatile contents of PSRs from orbit. These surveys have utilized a variety of methods like radar measurements, neutron spectroscopy, reflectance spectroscopy, direct imaging. But all these surveys have really generally concluded that the moon's volatiles are likely, spatially patchy or intimately mixed with the regolith or buried in the subsurface, rather than existing as these large, spatially extensive, nearly pure deposits. However, the real big problem with these orbital data sets is their limited spatial resolution, with one notable exception down here in the corner, which I will briefly touch on later in this presentation. For example, the polar temperature maps produced by the Diviner Lunar Radiometer are binned at about 240 meters per pixel, which is good for assessing regional or global trends, but really is averaging over a lot of interesting things that might be going on at smaller scales. This is particularly critical because surface exploration, either by crewed or robotic missions, will occur on scales a lot smaller than this. So there is a lot of interest in understanding what we might expect to see in advance of these missions. So this image here is sort of the classical example that I like to use to illustrate this problem. Over on the left is a DEM of the York University campus, which was produced by the Government of Ontario and has a resolution of 0.5 meter per pixel. Then on the right, I've degraded it to 240 meters per pixel. And so while you can see the general shape of the terrain is preserved, basically anything other than that is completely wiped out. So this work was really motivated by the work of Payne et al. 2021. So they looked at the effects of small-scale craters and surface roughness and how that affects the total cold trapping area on the moon. And so what they found is that about 10 to 20% of the moon's total cold trapping area might be in the form of cold traps on scales between about a kilometer all the way down to around a centimeter, which is the point at which lateral heat transfer tends to destroy the ability of permanent shadows to act as cold traps. So this work was really looking at permanent shadows on otherwise directly illuminated or sunlit terrain. And what we wanted to do was to extend this work into the PSRs themselves. Now, at first, this might seem like a bit of an odd approach to take because PSRs are, by definition, shadowed permanently, so long as you ignore things like true polar wander. But much like how the shadows that you cast here on Earth are not completely dark, the PSRs themselves are also not completely dark either, but are in fact illuminated by a number of secondary illumination sources, the most important of which is scattered sunlight, which you can see in this diagram here. So while the entirety of this crater here is in shadow, we can see that there is some scattered sunlight bouncing off of this directly illuminated crater wall and falling into the shadowed region here. Local terrain features can create these so-called double shadows that are protected from both primary and secondary illumination. And it is these double shadows that we are interested in here. So O'Brien and Byrne, 2022, tried to model these double shadows at both of the moon's poles and found that a very small fraction of the PSR area in both around both of the poles is doubly shadowed. However, these results are, again, limited by the 30 meter per pixel resolution of the LOLA DTMs that were used. They did go all the way down to the 5 meter per pixel DTMs right near the South Pole. But even these have, even this resolution limits the minimum shadow diameter to about 13 meters, which is pretty large on a human scale. We wanted to push even further than this, all the way down to 1 meter per pixel. However, the challenge that some of you may be aware of is that when you are going to high resolution, you are necessarily going to have to sacrifice the total spatial coverage that you have, simply due to limited computational resources. Given the total area of PSRs, as you increase the resolution of your maps, the number of pixels that you need to examine increases at quite an alarming rate. And so given the resources that we had available, we really wanted to limit our area of study to the largest area, or rather the smallest area that could still allow us to tell an interesting story. And so for that purpose, we chose the LCROSS impact site. So for anyone who may not be familiar, so LCROSS was this mission launched along with the Lunar Reconnaissance Orbiter to the moon in 2009 and consisted of two parts. You had the impactor, which was the expended upper stage of a Centaur rocket booster, and then the LCROSS shepherding spacecraft, which contained all of the relevant instrumentation. So the impactor was launched into the Cabeus crater PSR, and upon impact produced a large plume of material, which the shepherding spacecraft then flew through and was able to measure the composition of. So why did we choose this particular location for this work? Well, this is because LCROSS provided us with our first and to date really only direct confirmation of the presence of volatiles within a lunar PSR, as well as the relative abundances of the various volatile species that were detected. And so we can attempt to use our model to link the measured abundances from LCROSS with the modeled cold trapping area for each species. So to do this, there were three big steps that we had to accomplish. First, we need to take existing LOLA DEMs of the impact site and bring them to our desired resolution of 1 meter per pixel. Second, we needed to model the illumination incident upon the upscale terrain. In this case, we really focused on that singly scattered sunlight as well as thermal re-emissions from directly illuminated sunlit terrain. And finally, we needed to take that light and convert it into actual temperatures. So this here is an overview of our upscaling process. We begin with 20 meter per pixel DEMs from Lola, and then perform some basic 2D spline interpolation to bring it down to 1 meter per pixel. That interpolated DEM is then fed through a crater terrain evolution model to produce our final DEM at our desired resolution. Right, so let's take a look at each of those steps here. On the left is the original DEM of the impact site at 20 meters per pixel, and on the right is the upscaled DEM after interpolation. So while it is at our desired resolution, this interpolated terrain is very smooth in a way that the lunar surface is not, which is why we have to feed it through the crater terrain evolution model, or CTEM, which is described in Minton et al. 2019. So the CTEM is a Monte Carlo landscape evolution code that produces craters whose sizes are chosen from a lunar-like size frequency distribution. In this case, we actually truncated that SFD to minimize the production of craters that would be large enough to be visible in the original DEM. As time passes in the model, new craters are formed and old craters are degraded. And this terrain evolution model was allowed to run for about 3.5 gigayears. And you can sort of see here the progress of that terrain evolution as it occurred. Let's run that again because that's fun to look at. All right, so here is the comparison between the original DEM and our final upscaled and cratered DEM. So the illumination model that we used was really a pretty simple, pretty basic geometric illumination model. The exact details of them are not terribly interesting to get into in detail here. If you want to read about them, it is all in the paper. The one thing I will note is that we actually did not directly determine if a line of sight existed between the light scattering and the PSR terrain facets, again, mostly for computational resource limitation reasons. Instead, what we did was this 3-step process where first we took all of the light scattering terrain points, so these are the ones that are subject to direct illumination, and determined their elevation and azimuth as observed from the impact site. We then calculated what we were calling the local horizon on the upscaled terrain. This is not the actual horizon because it ignores everything beyond the extent of our upscaled DEM. But instead, it is an attempt to quantify the way in which the nearby terrain may impact the visibility of the further field terrain. And so if we overlay one of those local horizons on the positions of the light scattering terrain, we can determine which of the light scattering terrain points are still visible or not, or have been blocked by the more nearby upscaled terrain. The details of our thermal model, much like the illumination model, would not be terribly interesting to get into in detail here. Again, it's all in the paper. But we did use the semi-implicit thermal model that is described in Shorthofer 2024. Into this model, we used the temperature and depth-dependent thermal physical properties of the surface. So this would be density, heat capacity, and thermal conductivity, which were adopted from the low-temperature thermal model of Martinez and Siegler 2021. So that model was actually developed specifically for the low-temperature regime that is often seen within PSRs. In some ways, it may have been more ideal to use that model, but at least in our experience, it ran a bit more slowly, which, given, again, the time and the computational resources we had available, was a bit of a drawback from us. However, if we compare the outputs of the two models for the same input, we can see that they are, they follow each other relatively well. Although the model that we use tends to slightly over-model the minimum temperatures and slightly under-model the maximum temperatures. All right, so this is the big high-level picture here. On the left is a hill-shaded terrain our upscale terrain of the impact site. And on the right are the maximum temperatures experienced by that terrain. Unsurprisingly, nowhere is particularly warm, but you may see all around the surface are these, these black areas of varying sizes, and these are these micro ultra cold traps, so these craters that are doubly shadowed, which have exceptionally low maximum temperatures, and they cover about 3% of the surface. So when we had this when we got this result, the first question we asked was, are these temperatures reasonable? So we attempted to answer this question by modeling what diviner would have measured if it were to observe our surface. So we did so by creating a linear mixing model of 57,600 blackbody spectra. And you can see the results of that here with the diviner measurements of the impact site in red and our modeled temperatures in black. You see in this area, they follow pretty well, but over here, there is a fairly noticeable, substantial difference between the two. So this area of under model temperature at this time, is actually noted by a number of other papers looking doing thermal modeling of the impact site at lower resolutions. A number of potential causes have been put forward, such as anisotropic thermal emission from sunlit surfaces, as well as an instant angle dependent albedo. We did not attempt to answer why this temperature difference has occurred, but we can say at the very least, we appear to be consistent with other models at other resolutions, if not necessarily entirely consistent with the diviner measurements themselves. So something else we looked at was the seasonality of temperatures. And so this is because, while we do like to, present the maximum temperature as, the absolute highest temperature that various volatile species can be stable. In fact, that's not necessarily the case. I mean, the stability threshold for each species is, to a certain extent, a bit arbitrary. And brief excursions above that threshold, may not, in fact, lead to the total destruction of any surficial deposits at those locations. And so what we can see here is that actually, most of the surface spends a significant amount of time below its maximum temperatures. Now, if you look down here at the bottom right, you can see that basically the entire surface spends over 90% of the year below 45 Kelvin. And a significant portion of the surface spends over 80% of the year below 40 Kelvin. And so again, this does indicate that time average sublimation rates are likely a better indicator of stability than the maximum sublimation rates. Something else interesting that we can note is, comparing the relative abundances measured by LCROSS to the fraction of our upscale terrain that each species could theoretically be stable across. And what we notice here is that the total cold trapping area does not appear to be driving volatile abundances. For example, if you compare water, ammonia, and sulfur dioxide, they all have very similar available cold trapping areas, but were detected by LCROSS at vastly different abundances. Similarly, hydrogen sulfide has only about half of the total cold trapping area, but was detected at a much higher abundance than either ammonia or sulfur dioxide. And so this does seem to be consistent with the story from orbit, that although the moon does have ample cold trapping area, those cold traps are far from full. The final thing we did was to try and look at the implied surficial source abundances. So this was linking the measurements from LCROSS with the cold trapping areas that we modeled. So we defined the abundance per stable pixel, which is a quantity that basically answers the question of how much of each species is needed in the areas where there are stable to explain the LCROSS measurements. That is, for example, if there is a particular volatile species that is stable only in a very small region on the surface, both detected at high abundances in the impact plume, then that small stable region must have contained a significant amount of that species, and vice versa. The important note here is that this approach assumes that all of the volatiles detected by LCROSS were sourced from surficial cold traps, which is almost certainly not the case. And so this is the potentially slightly hard to interpret figure about that. So you can see the relative abundance of each species and how it varies across the surface depending on exactly where LCROSS impacted. So we can see that, much like how the temperatures themselves are very spatially variable, these implied abundances are very spatially variable as well. This is maybe a slightly easier way to interpret those data. Just looking at 4 locations on the surface and the relative abundances needed to explain the LCROSS measurements. For example, if you look up here in one of these warmer regions, we see about equal portions of H2O and H2S, whereas everywhere else tends to be more H2O dominated. If you look, within one of these micro ultra cold traps themselves, you tend to see less C2H4 than elsewhere on the surface. And so you can see basically what we're saying here is that, depending on where exactly LCROSS impacted, on this surface, we could have, very different stories about what the actual in situ volatile abundances may have been. The final bit that I'll note here, which was actually not in the paper as it was not available when we were writing it up, is that we now do have actual images of the LCROSS impact site from ShadowCam. So you can see here our modeled surface compared with a ShadowCam image. And so the exciting thing here is that these high resolution, about 6 meter per pixel DTMs from ShadowCam will allow us to hopefully verify or at least refine these results by minimizing our dependence both on the upscaling process as well as the CTEM. Right, that is all that I have for you today. So I am open to taking any questions that you may have. Thank you.
Awesome. Thanks so much, Connor. And yeah, I see you have some applause in the participants list. But yeah, what questions do folks have? And I see Erwan has hand up. Yeah, go ahead, Erwan.
Hi. Can you hear me? Yep.
Yeah.
Thanks. I have a question for you related to your method for determining the contributing surface to the in terms of thermal. Because from what you showed, with the different horizons that you break up, you take the nearby field, right, to occlude the far field.
Yes.
But so does the near field ever contribute radiation to the pixel you're looking at?
It does not, which is one of the things that we note that, obviously, the near field terrain in reality is going to contribute some additional scattered light as well as, these thermal emissions into the terrain itself. So in reality, our temperature are probably slightly below what one would expect to see just because we're ignoring all of those additional surfaces.
I guess for those double PSR areas, right, that you don't have that have very low temperatures, I think even a little bit of radiation that's reflected off the nearby crater slope, right, could and I don't know how much, right, but could potentially raise the temperatures. So that was my question. Thanks.
Great. And I see Paul Lucy has hand up.
Hi, Connor. Can we go to slide 16? Can we go back to sharing?
Yeah, hang on just one moment. Slide 16 is this one.
Yeah, so the top trace is that the reflected and emitted light from illuminated terrain nearby?
Yeah, so this is this plot comes from the data in the Martinez and Siegler paper.
Okay. I'm just surprised because not your problem, but only indirectly. But I'm really surprised that the thermal emission is so high compared to the scattered sunlight. All
This is
the
also not within not at Cabeus either. This is, I believe, at Shoemaker.
Yeah, but in general, those two terms should be pretty similar unless you have crazy high albedos. So, anyways, but that you're using that as an input to your model.
So this was just we did not actually use these particular data in our results. This was just to create a comparison of the performance of the two thermal models.
Okay, I see. Okay, can we go to 19 for a sec?
Yeah, this one.
Yeah, I just want to make the comment that the maximum temperature, limit, agreed. It's it's a rule of thumb or a shorthand, though, because the sublimation rate is exponential. A very short amount of time at high temperatures is a lot of sublimation. So I think it's despite the fact that you might only spend 5% of your time at those high rates, that's still a huge amount of sublimation. So, some kind of agreed the time average sublimation is a more accurate indicator, but I think the maximum is still not too bad. But now that we can actually model it, that's fine. I just want to make that comment. And then one last thing, slide 23.
Nope, not this one. This one.
Yeah, I'm confused why. What's causing this variation? So, are you assuming the LCROSS flux was present at the surface at some time and then evolved to that state? Or I'm not
So
seeing
this,
something special about that H2O rich site compared to some of the H2O rich sites.
yeah, this is just basically comparing the total cold trapping area. So for each of the species. So again, so if you have, for example, an area where there's only a very tiny cold trapping area, but if LCROSS detected a large amount of a particular species that is only stable in the area, then that implies necessarily that that area would have a very high concentration of that species in order to produce that result.
Okay, I'll have to read your paper. All right, that's it. Thank you very much.
Hey, Connor, actually, while you had that slide 23 up, I had a question about that. So I know this made sense to me when I read the paper, but that was last week. So just to make sure I'm or to check if I'm interpreting this correctly. So it's like so you have different pie charts for each region, and is the area in the pie charts the fraction of area within that small region where ice would be stable, or is there another factor in there?
This is the relative abundance of each species on the surface at those locations that would be necessary to replicate the LCROSS results.
Okay, and the reason it varies from site to site is because the local temperature distributions vary.
Yeah, so the temperature varies spatially, and so the total cold trapping area for each species also varies across the surface.
Okay. Okay, so just and this is like I should go back and read the paper again. But so like if I look at one of the pie charts, so let's say like I look at the one in the top left. So
Yeah.
I see that about like half of that is H2O. So is that saying that half of that in order to explain the LCROSS abundance, half of the sites where H2O is stable at that location would it have to have been occupied by H2O? Is that the
This
right
is,
way to?
I guess it's more like the relative abundance of each species at that life. So you can see here, like H2O is about half, and then H2S is about a quarter. And so that would say that to explain the LCROSS results, if everything was just at the surface, this site, that H2S would be about half as abundant as H2O.
Okay. And let's see, I see. So Rick Elphick had a comment in the chat that LCROSS abundance is of large uncertainties, especially the non-water species. So the pie charts may not be that distinct since they could all be within the LCROSS error bars. And then Norbert had a comment to Paul Lucy regarding the IR visible irradiance ratio. If the albedo is 20%, then 80% is emitted in the infrared, more or less. All right, do we have more questions? Yeah, I thought this was really interesting, and like the comparison of the relative fractional area of the temperatures to the relative abundance of species in LCROSS was interesting, like because I wouldn't have known beforehand what to expect. Like it would have been interesting if it had lined up perfectly, but it's also interesting that it doesn't line up perfectly. So that's cool. And Caleb, you have your hand up.
Yeah, hi Connor. This is sort of a plug, but I just got a paper accepted in GRL, I guess last week or 2 weeks ago, that actually shows where we think the LCROSS crater actually hit. Yeah, you mentioned that DTM that Madeline Manheim made will allow some new look at this. Hopefully, I look forward to seeing you just run this on the actual topography, and it looked to me like the crater formed on top of a bunch of other craters, so that really might speak to your story a little bit.
Yeah, that will be very interesting to see. Very much looking forward to getting hands on those DTMs.
Yeah, I'll send you since it's accepted, I'll send you a reprint after this call.
All right, and some more comments in the chat. Sarah Soul says, great talk. Rick Elphick says, good study. We should send a mission to the lunar South Pole, go into some PSRs and see what's going on in there. Yeah, for sure. Yeah, I mean, I've always thought it would be really interesting to go and visit the LCROSS impact site and see what that looks like now.
Definitely going to be, interesting over the next, number of years, actually taking these from, what we think might be there to actually, going and looking and seeing what actually is there.
Yeah. Do you think you might do something similar for like future landing sites? Like, are there observations by upcoming missions that might help test some of various aspects of this?
I mean, I guess we were all sort of looking forward to Viper and that sort of, first look into what's actually on the surface. Obviously, the condition of Viper at this point is now uncertain. So, I mean, hopefully we don't have to wait all the way until, Artemis 3 or 4, as it may be, to actually get, boots regardless of whether they're human or robotic boots on the ground to actually measure these things.
Yeah, and I guess I don't know if we have anyone from the LCROSS team on, but I know there's so Paul Hain has an instrument LCROSS, which is sort of think it's basically a thermal infrared camera that would sort of image the surface at those sort of really small scales. So I guess that temperature distribution would be interesting to compare to your stuff. Yeah, and Jen points out that there was a National Academy's concept study for the recent decadal survey to send a rover to revisit the LCROSS impact site and other locations of interest. Cool. Great. Do we have more questions? I guess to give folks a little more time to think. So in terms of like, do you have sort of next steps for this work, or is it kind of, I mean, I know you mentioned maybe using the shadow cam data to sort of test how well the upscaling of resolution works, but are there like what's next for this work? I mean, it is like a very nice self-contained study, but yeah, do you have thoughts of other things you'd like to do with this?
I mean, there are all sorts of, refinements that one could make. One could, again, try to, more precisely measure the contributions of the near field terrain on the temperatures as well. Could expand it to, larger areas, other areas that may be of interest, like example, to the Artemis missions. It's all really just a question of, the computing resources that I have available to me. So, expanding any of that is, very rapidly expands the the resources required to do so.
Right. Yeah. Yeah. That makes sense. Any more questions? We have plenty of time for questions. So if folks have more. Though if not, that's fine as well. And I am going to put the link to the paper in the chat so people have it. It was in the email as well. But yeah, but if folks don't have additional questions, oh, Paul Lucy.
Maybe I'm jumping the gun on the agenda, but since we have Halloween coming up, I thought a fun theme for us might be to bring up all the scary things we worry about, but we think that skeleton might be buried in the closet. Like, for example, we're linking so much analysis to the LCROSS estimates. Rick pointed out that those are pretty uncertain, and so that's just one of a lot of things that are in our anxiety closet. So we could have a scenes of lunar volatiles theme for October, maybe.
Yeah, I was yes, I was gonna cancel October's meeting because it's the week of DPS.
Because
And
you're
then
scared.
I know, yeah, yeah. Like busted. But no, let's yeah, let's but I like that. So yeah, so fiends of lunar volatiles. Yeah, so what's your greatest fear, Paul? That we're tying a lot to the LCROSS.
That's now you put me on the spot. That's one of them, but I know I have a lengthy list. But it would be kind of fun for people to say, even if it's like maybe this is not my field, but I really worry about our dependence on this or the quality of that or that kind of thing.
Yeah, does anyone else have another one?
Well, I kind of mentioned the mismatch of these thermal models and what's going on here, and how bad, for example, if the models are not matching the measurements in some places, what are the bad implications? The how important is that to really understanding what we're going on. Are we over-interpreting, any measurement because it's sui generis? Another one is the LADI water atmosphere measurement, which is entirely dependent on the NMS, and it was a really tough measurement. But a lot of things are linked to that number, similar to the LCROSS. So we have sui generis measurements that ought to be repeated or confirmed or something. So that's kind of because I run into this problem, what I do is the LCROSS measurements and the LADI atmospheric water measurements are critical numbers, but they're dependent on a single really tough measurement.
Yeah, I was trying to think what I don't have any fears. Like, whatever the measurements show, I'll tweak model parameters apparently, but or appropriately. But Michael Postman says phase angle.
Yes, so much of it's not as relevant to this talk, although it probably factors in ways I haven't thought of yet. But so much of the what's there in like the infrared especially is where we have a lot of measurements, but in the LAMP data as well. All those remote sensing measurements are the interesting stuff happens at the spots we don't work in as often, and that scares me.
Yeah, well, this got depressing really fast. Thanks, Paul. And then Connor, to be clear, like these aren't fears about your work specifically. This is this is like what keeps other folks up at night. And yeah, Tim Livengood, fairy castles. What's going on with the fairy castles? I like the fairy castles. But yeah, so
I would like to see a picture of one.
yes, I would
In
love to see
reality,
a picture of one.
right now they are purely theoretical constructs. I would like to see a dang picture at the appropriate spatial scale, like micron resolution, of an actual fairy castle, because so much of planetary photometry depends on assuming they exist.
So there's this like I went looking for pictures of fairy castles, and for folks who like are wondering what the context for, so fairy castles, the small scale regolith structures which may have towers with sparkles. But so there's this Hapke and Van Horn paper from 1963 or something, and so they have some really nice images of not fairy castles on the lunar surface, but it's sort of these really close-up images of like, I think, flour and some other material, Portland cement. I'm not sure what that is, but basically like they have some sort of microscopic images of like what looked like fairy castle structure and some of these regolith analog materials. But yeah, it would be very cool to see those on the lunar surface. Ha. All right, so next year we'll do a Fiends of Lunar Volatiles October special session. But in other news, so DPS is coming up in a few weeks. Does anyone have any work that they're planning to present at DPS that's relevant or not relevant, but might still be of interest to this group?
I have a presentation in the Earth Moon section looking at the 3 micron band, so OH and H2O, using Chandrayaan-2 spectrometer.
Cool. Awesome. Thanks, Chris.
Not me for DPS. I'm holding out for AGU.
Mm-hmm. What are you presenting at AGU, Tim?
I'm going to be talking about our instrument development work at Goddard, and possibly something new if I'm allowed to talk about it by then.
All right. Intriguing. Yeah, I won't be at AGU, but I have a DPS talk in the Mercury session, which is an update on some modeling that I've been doing to see if a comet impact could explain the water ice that we see at Mercury's poles. And so basically we've been considering this one candidate impact and running a simulation to see, you know, if this impact was responsible for delivering water to Mercury's poles, what would the distribution of water look like? Does it match what we see in observations? Are there any interesting patterns that future observations could look for, and so on? And I guess also potentially relevant to this group. So next week, there's a lunar surface science workshop on plume surface interactions that I think I might have seen some familiar names on. But is anyone presenting anything there that they'd like to talk about?
There's a talk out of Goddard, Dan Kremens and et al. Will be talking about laser measurements of plumes from the surface, compositional and possible scattering. So there's a kind of an instrument section of the workshop, and he's in there.
Mm-hmm. Yeah, and I think I saw a few other abstracts in there as well that looked relevant. And I know a couple of us are giving talks on modeling. So me and William Joe, who's online, maybe others as well. All right, so last thing while I have folks online, I just wanted to advertise our Google Drive, just so everyone knows it exists. But so this is a Google Drive, but basically you can access it via this long link or this short link, tinyurl.com/FOLV-drive. But it has calendar invites to meetings. There's the meeting schedule, so you can even look back at previous meetings. So we won't meet in DPS. We tentatively have something lined up for November. And then I think December, given AGU and the holidays, we'll probably take a break as well. But then there's also there's this expertise directory that we set up a while ago, but it might be useful if you're looking for people to suggest to review your recently submitted paper, or if you're looking for seminar speakers or collaborators or anything else. And this is crowdsourced, so feel free to add your name if you're not on there already. And then there's subscription information, and it's definitely not a complete list. I try to add to it occasionally, but it's intended to be a crowdsourced list of recent or even not recent papers related to lunar volatiles, and we can put additional things in there. But there were a few of these spreadsheets floating around, so I thought I'd put them on a Google Drive. And if folks have suggestions for other things that might be good to have on there, let me know, and we can get those on there.
Is that link in the emails you've been sending? Because I've definitely had the calendar invites drop off my calendar again.
Yeah, the calendar invites, like, it's
Just none of
stopped
the
it.
ones from APL have been working for my calendar. Like, because with some of the other
Right.
stuff that APL is leading meetings from, they're all really wonky too. Just, I don't know, something
Yeah,
between
yeah,
your system and our system doesn't talk for me.
yeah. So a couple of folks have mentioned that, like, and so attaching the calendar invites does funny things sometimes. But here, I'll put the link to the
Oh, it is in there. I just had to
drive
read
in
more
the
carefully.
the chat. Yeah. But yeah, but I'll try and make sure to update the calendar invite in the drive so people can at least download it and add it to their calendars, which might be more foolproof than relying on Outlook or Gmail or whatever to do it. So I didn't have anything else on the agenda today, but yeah, folks are kind of quiet today, but that's okay. We can be quiet sometimes. But yeah, anything else volatiles related that we should talk about? Or non-volatiles related? I guess the latest on Viper. Oh yeah, no, go ahead,
Oh, I
Michael.
mean, I'd rather hear Viper.
Okay, yeah, no, it's no, so the latest on Viper. So I think the House, the U.S. Congress House Committee on Science Technology, I forget what exactly it's called, but basically Congress has sent a letter to NASA asking for more information on the decision to cancel Viper. And if I can find it, I will put that in the chat. But yeah, what were you gonna say, Michael?
Oh, I think it was Rosemary sent out a couple of papers. I didn't have a chance to look at them too closely, but I read the titles and they looked very relevant to this group, and to something I've been thinking about a lot, which is how much the kind of how much making the measurement changes the result of the measurement, to put it in a kind of obtuse way. Going and landing, I've been saying for years now, we need to be able to land and then drive away from where we landed, like Viper was going to do, to really know what the natural moon had. And it might even take several lunar days, even once you've driven away. So I'm looking forward to reading those two papers that Rosemary sent and seeing if they address this or if there's still more work to be done.
Yeah, they're interesting. The first paper on how much of an atmosphere do you form around a lander, which is certainly something I've been thinking about for a while, but flailing at. So it's good that we have something that is calculationally careful. And then the second one was more about something I've talked with one of the co-authors, Caitlin Ahrens, about before, the ethical issues of our intrusions upon the moon and how it alters the lunar environment, well, not just ethical, but how it affects anything we would do further in the future.
Yeah, I saw that table in one of the two attachments where it was like, here's the science that our pollution, if you will, makes it much harder to do, versus here's the science that doesn't really seem like it's likely to be too affected by say a human leaning over or maybe turning their back and having all the water from their sublimator collect on.
Yeah, I had
and
not known
I read
about
that as
that
a
till
science
Patrick told me
prioritization.
about it.
Yeah, same here.
Yeah.
I hadn't, or I kind of interpreted that table, having not read the paper, as a prioritization of what we need to do first before we've contaminated it too much versus what science can wait until later missions.
One of the challenges is when we were working on a sort of a concept study here at Goddard, we realized that we actually couldn't get anybody to go on the record about how they plan to cool the EVA suits for Artemis. Are they going to be using a water sublimator like the Apollo suits? Nobody was willing to say it publicly, either yes or
LPSC
no.
2023.
Well, okay, that's a couple years after we were looking at it.
Spoke
Thank you.
in response to that question, like just at the microphone, they said, I believe it's sublimation again. But I don't think I've seen anything in writing or an official talk, just kind of conversation at conference level.
Yeah, I mean, we were asking people like Kelsey Young, who should be able to tell us the answer, and she was very circumspect about it.
Well, weren't they outsourcing the suits? So it wasn't really, if it wasn't
Well,
in the contract,
that's
it wasn't
the case
NASA's thing.
more recently, yeah.
I mean, maybe we'll have to attach radiators to all of them instead.
Well, I think the reason for the sublimator is that the radiator has to be big, and of course, sometimes the sun shines right on it. And so then you get the opposite effect, and you don't want that.
Right, yeah. Astronaut carrying an umbrella thermally tied to their suit might get very hot if they point it the wrong way.
Well, it is time for me to run.
All right. And on that note, we are almost at the top of the hour. So so thanks again, Conor, for a great presentation. Congratulations on the paper. And yeah, thanks everyone for dialing in. And so we won't see each other in October. So maybe we'll think about each other on Halloween. But yeah, otherwise we'll meet again in a couple of months from now. Take care, everyone. Bye.